I'm David and I'm presenting Multilingual Nonce Dependency Treebanks, which we use to investigate how autoregressive and masked language models represent and process syntactic structure. This is joint work with Laura Kalmeier, Yunus Sami and Hassan Sajjad. An ample amount of work in the last few years is focused on making the linguistic information of language models explicit. The idea is usually to analyze internal states of models, focusing on representations, or analyzing language model predictions, focusing on behavior. A subset of these works focus on syntax, and specifically on the question how hierarchical tree structure is encoded by language models. A difficulty there is separating grammatical knowledge on the one hand from semantic information, lexical occurrence on the other. We address this difficulty by using nonce data, which is data that is grammatically correct but nonsensical. A popular example of this is Chomsky's colorless green ideas sleep furiously. We contribute to the topic in the following way. First, we present the dataset of semantically perturbed universal dependencies, or SPUD, that allows us to separate syntactic and semantic information by creating syntactically annotated nonce data in 5 different languages. Using this dataset, we show that masked and autoregressive language model perplexity scores respond to semantic perturbations differently. We also explore the effect of this dataset on the performance of structural probes, which extract syntactic trees from language model representations. We work with 5 different languages, namely Arabic, English, French, German, and Russian. Even though this selection is relatively small, it features widely spoken languages from different families with different writing systems and other linguistic features. In principle, this can be extended to other languages relatively easily if a UD treebank and access to a native speaker are available. The main idea behind the dataset is that we take existing dependency treebanks and create parallel, semantically perturbed versions of the sentences. In the example, the English UD treebank contains the sentence "I'll post highlights from the opinion and dissents when I'm finished." Versions of this sentence are then created which contain different content words but have the same syntactic structure. For example, "I'll ban statues from the shape and wheels when I'm Saudi." The data is created in this way. The data created in this way is grammatical but nonsensical, as you can see in the examples. The perturbations preserve argument structures. For example, the transitive verb post is replaced with other transitive verbs. Argument types, on the other hand, are potentially violated to different degrees. For example, in certain contexts, it might make sense to talk about banning statues, but it is unclear what it means to ban statues from the shape and wheels. The part of speech tags affected by these replacements are nouns, proper nouns, verbs, adjectives, and adverbs, so basically all content words. And as a consequence, the nonce sentences have much less useful information in terms of co-occurrence of words. The dataset is created in 2 stages. First, there's a language-independent component that replaces words based on the syntactic context they occur in. In the example, we have the sentence, "The service was friendly and fast," and the subject noun service has one determiner dependent. We replace it with interior because interior occurs elsewhere in the treebank, also as a subject noun with one determiner dependent, with matching morphosyntactic features. The same idea is applied for the adjectives in the example. And this replacement is language independent, and to ensure that the output is grammatical, some language-specific modifications are applied. For example, when changing "Chris eats an apple" to "Chris eats a bicycle," we check a phonological dictionary to make sure that the determiner and the noun match. To ensure the quality of the dataset, linguistically trained speakers annotated chunks of 100 sentences to point out errors during the generation process. We conduct a small human evaluation on German, English, and French. It shows that including dependency information and language-specific rules really helps grammaticality. Next, we will look at how language models process this data. We use 2 kinds of language models, namely masked and autoregressive. We are interested in the difference between these because their predictions are based on different amounts of context. While an autoregressive model processes a sentence incrementally, a masked model has access to all other words when predicting a masked token. Previous work has tried to empirically relate the perplexity of autoregressive language models to the perplexity, or rather pseudo-perplexity, of masked language models. The perplexity of an autoregressive model is defined through the average likelihood of all correct next word predictions during one pass through the sentence. And the masked language model perplexity, or pseudo-perplexity, is on the other hand computed by masking out each token in turn and averaging the scores of all ground truth tokens. This is different because each prediction is based on the same, rather than an increasing amount of context tokens. And this leads to multi-token words having inflated scores, because the subword tokens of such words have a high interpredictability. To mitigate this, we also evaluate the masked models on a score proposed by Kauf and Ivanova, in which multi-token words are generated incrementally. They show that this left-to-right or subword-aware pseudo-perplexity is empirically more aligned with perplexity, and we want to test if this is also the case on nonce data. Concretely, we want to know whether SPUD is harder to predict than the original data. This serves mainly as a sanity check for the dataset. Co-occurrence information is perturbed, so we expect that the data is hard to predict. We want to know whether in general autoregressive models are affected differently by SPUD than masked models. And for masked models, we want to know whether the two versions of pseudo-perplexity are affected differently by SPUD. We test these questions by first obtaining language model scores on the original and nonce data. Because the perplexity values can fall in a relatively wide range, we use the ratio of perplexity values as a measure of the effect of SPUD. For example, we see here that their schedule is listed below receives a perplexity of 406, while the perturbed version, their film is listed best, receives 4545. The nonce sentence perplexity is thus 11.2 times higher. We use the models Multilingual BERT and MGPT. The paper also contains some experiments with monolingual models. To mitigate the disadvantage of autoregressive models on very short sentences, we remove sentences shorter than 4 tokens. This results in dataset sizes between 5.6 thousand sentence pairs for Arabic and 144,000 sentence pairs for German. The first question is whether SPUD is harder to predict than original data. We show here the score ratio distributions for Arabic at the top and English at the bottom. And we see that for almost all sentence pairs, the ratio is above 1, meaning that the nonce data is harder to predict. Second, we test whether the autoregressive scores are affected differently by SPUD than the masked scores. This is also the case. LLMs have significantly higher scores than masked language models, as confirmed by a Wilcoxon test. Finally, we test whether the two versions of pseudo-perplexity are affected differently by SPUD. We see that for English, German, French, and Russian, the increase in pseudo-perplexity is smaller. Only for Arabic, the increase in pseudo-perplexity is larger than for the subword version. This means that for 4 out of the 5 languages, the left-to-right pseudo-perplexity is more aligned with autoregressive scores. All the differences are significant and generally as expected. The interesting case of Arabic could be due to a number of reasons such as writing direction or word structure and tokenization. Summing up this experiment, we've seen that first of all, the health check for SPUD is passed. The nonce data disrupts lexical co-occurrence as measured by perplexity and related scores. We have also seen some non-trivial differences between the behavior of autoregressive and masked language models on nonce data. In particular, autoregressive models are more affected by SPUD, most likely due to the fact that they have less context available in the predictions. Finally, we see that the empirical difference between pseudo-perplexity and subword-aware perplexity mostly carries over to nonce data. The second experiment considers our intuition that the nonce data should have the same syntactic structure as the original. We asked whether language model internal representations follow this intuition. We do this via structural probes, meaning that we extract dependency trees from the internal representations of the models using a relatively simple parse tree decoder. We train the probe on the original data and test it on both the original and the nonce. The performance drop on the nonce data is a measure of how well the probe generalizes and of how much the probe relies on semantic, not syntactic information. The probe we use for this is DEP probe, an architecture presented by Müller-Eberstein et al. 2022. It is essentially an extension of Hewitt and Manning structural probes to directed and labeled dependency trees. The trees are evaluated in 3 ways. The unlabeled attachment score measures how many tokens are attached to the correct head, irrespective of the label. The relation labeling accuracy measures how many dependency relations are predicted correctly, irrespective of the head. And the labeled attachment score measures how many tokens are attached to the correct head with the correct label, evaluating the whole tree. For the experimental setup, we copy all settings from Müller-Eberstein et al., who probed the mid-layers of multilingual BERT on 13 languages. We again test on all 5 languages and compare the performance of autoregressive and masked models on original and nonce data. For the results, shown here for multilingual BERT, we see that the absolute performance is mostly determined by the treebank size. Delta is the absolute performance drop on nonce data. It is generally larger for attachment than for relation labeling, indicating that relations are more easily extracted from lexical cues than attachment. However, in the end, the overall performance is still quite high, even on nonce data. When comparing multilingual BERT with the autoregressive MGPT, we see that the ALM is almost always worse. The exceptions are circled. The good performance of MGPT on Russian is unsurprising, given that the model training data puts special emphasis on Russian and related languages. We also see that the performance drop is usually larger for ALMs than for MLMs. The mean drop in LAS is 4.76 for Multilingual BERT and 8.16 for MGPT. In summary, DebProbe can decode SPUD trees with some performance drop but generally good results. Trees are better decodable from MLMs than MLMs, and the incremental processing of autoregressive models leads to them being more affected by SPUD, and also generally worse results in terms of predicting attachment. The paper contains many more experiments regarding layer effects and some baselines and monolingual models. To conclude, we have presented a framework for creating high-quality parallel nonsensical UD treebanks and applied to 5 languages: Arabic, English, French, German, and Russian. A variety of use cases for this data are possible, especially in the context of data augmentation or syntactic similarity benchmarks. We show 2 use cases related to the behavior of different language modeling architectures. First, we contribute to the question of how best to compute scores from masked models. In MLMs, while we find that the empirical difference between subword-aware pseudoperplexity mostly carries over to nonce data, we also see that autoregressive models are more affected by nonce data overall. The fundamentally different ways autoregressive and masked models access context impact their scores on nonce data. This result is strengthened by a syntactic probing experiment in which we see that a majority of the probe performance is retained while testing on nonce data, but autoregressive models suffer a larger performance drop than MLMs and also perform worse in general.